Welcome, and thank you for joining us for today's Ask the Experts presentation brought to you by Qualmark's Center of Excellence. I am Gail Ecker, Director of Marketing for Qualmark, and I'll be the webinar moderator. Today, Qualmark Center of Excellence is hosting the fourth webinar in a series on highly accelerated stress screening, otherwise known as HASS. Links to the recording of the previous webinars in this series, Part 1, Streamlining HASS Implementation Leveraging HALT Data, Part 2, HASS Fixture Design and Integration, and Part 3, HASS Proof of Screen, are all available on the Spotlight section on Qualmark's homepage, www.qualmark.com. Today, Neil Dortenbaugh, Qualmark's Senior Application Engineer, discusses HASS integration. Welcome, Neil.
Thank you, Gail. I'll give you a brief idea of what we'll be covering here as we talk about the key aspects of actually integrating HASS into your facility. I suspect that everybody here has good knowledge of HASS. We'll just touch on a few key slides there. And then I want to move into what is involved in the total HASS integration project and why it needs to be a project. It's a multidisciplinary task to bring HASS into a facility. We'll spend some time discussing the physical integration, what it takes, what considerations there are for liquid nitrogen, air venting, that sort of thing, as well as selecting the right system for your product. And then we'll spend some time talking about how to integrate HASS into the production test plan. Not just from a process flow standpoint, where do I put the HASS in my process, but how to get the most value out of the HASS results. And this is really a key portion of what I want to discuss today, and we'll spend some time there as we reach the end of the presentation. As Gail said, if you have any questions, feel free to type them in. We'll have a question and answer period at the end. And just for fun, I do like to start these off with a quick poll. So we'll take a few minutes now. If you'd check off on the poll that you see here, what the level is of the HASS performance that you're doing now. If you aren't doing any HASS, all the way up to you're thinking of getting it started sometime in the next year, just to give us all an idea of the level of use of the technology amongst the folks that are listening. So we'll wait for the respondents to tick up there. We've got about 20 folks that have checked boxes already, so we'll give it another few seconds and see what we have here. We have an interesting spread, it looks like. I appreciate everybody, if possible, checking something off there that's applicable. And let's see here. Looks like that's just about everybody that's going to click a button, so let's go look at the results. And you can see here, we've got a little over a third of you that are doing HASS now, and a little under a third that aren't doing any HASS. The rest with plans to get some HASS started before too long. So that's good news. That's a good spread. We've got folks who know what they're doing and folks who are trying to figure it out, and I hope to help all of you as we go along. So, a brief discussion. What is HASS? What are we trying to do with a highly accelerated stress screen? Really, a primary focus here is we're detecting and correcting process changes. There's two places where you can make mistakes in a product. You can design in something, or you can have something happen after your design is finalized. And HASS is intended to address that second portion. Find things that have changed in the process or in components that can compromise reliability. And do it fast. You want to get production time down and production cost down. And in that process, of course, get your out-of-box quality up and field reliability up. With field reliability up, warranty costs go down. Field service gets to actually take a vacation every now and then. And when you introduce a new product, HASS can be especially valuable for stopping those upsets that can occasionally happen when you first get production into high gear. At least stop them from hitting customer hands. You'll find failures that you can't find with burn-in. As many of you know, burn-in doesn't do a whole lot anymore because we figured out how to make ICs, and the purely chemical processes that burn-in spots aren't a major factor in what makes products fail in the field. But the vibration and extremes you use in HASS do find those failure modes. So you can very quickly find process and component problems. And one last point, HASS really is not a fixed test. It is a process. Each product will have its own process. It doesn't, it can make perfectly good sense if you have a burn-in plan to reproduce it for all your products. But with HASS, it's dedicated to each product because the limits that you use in HASS are based on what you learned in HALT. And we've been through that several times, I'm sure, so if there's any questions on it, you can refer back to some of our past webinars for details on how we get to that level. And HASS can change and will change as the product matures in the field. You can back it off, make the modifications necessary to save time and money when you can in production. This is a slide that some of you may have seen before from Qualmark, where we talk about all the different places in a product's life cycle where HALT and HASS can be used. This is really the area that we're addressing today when we talk about the use of HASS. We talk about in pilot build, you're doing your HASS development. Once you get into full production, of course, that's where you've set up the HASS screen. And also, if you have a contract manufacturer, implementing HASS at the contract manufacturer is an extremely valuable way to use the technology. Now, there are other ways. Over here, for example, at the field depot, that's a good place to use HASS as well, but that's really not what we're talking about here. We're going to be talking about the production aspects and how to get it set up and going in your facility. Now, one thing you don't want to do is approach HASS too casually. You need to have a project plan in place to get HASS integrated well into your facility. There are many disciplines that are involved. Of course, the facilities folks are involved. Manufacturing is involved. Design is involved, the level of implementing the HALT and making sure that those corrections are in place before you begin HASS. You really need to define a team, define a project manager, and treat this like a real project. When you do that, you're going to get the process implemented as quickly as possible and with as few hiccups as possible. And as you implement this team, you can come to Qualmark for assistance in what the steps are and assistance in the process and the facilities requirements as well. One of the things we definitely recommend is some classroom education for folks that are being involved in HASS for the first time. HASS is something that is new for a lot of people, and spending some time in a classroom, understanding what the goal is, the concept, and where you're going will help you set up that project team with the right people, make sure you have your engineering tasks understood, get your budgeting done right. You don't want any surprises in budgeting at the end, and that you have the people you need and the facilities requirements all set up. So a day of classroom education is something that Qualmark offers. Come in and do a seminar, talk about all the basics, doing what you have to do in that HALT when you're setting up your HASS screen. Make sure the theory's understood. We'll go over fixture design and validation information, and of course, how to set up that screen and prove it, and then talk about how to get the units actually implemented in your facility. The whole process of the development of the HASS screen will start out often with the fixture design, where you're figuring out the way to get many products fixtured into a chamber. For HALT fixturing, it's pretty easy. You're just doing 1 or 2, sometimes 4 units, and it's not really critical that it be exactly reproducible, and you can enjoy the privilege of damaging product if you see fit. With HASS, it's a little bit different. Fixture design becomes more complex. We have to make sure that we have designed a system that has equal thermal and vibration excitation for the products being tested. We do that as the fixture is designed. If the fixture is designed here at Qualmark, we'll repeat that on site so that we can do what we call the installation qualification, and then a full integration qualification where we're making sure that things like ATE that is linked to the Qualmark control system is functioning properly, and we look at the human interaction and the ergonomics of the system and making sure that everything is coming together as expected. And screen development, proof of screen are all part of that once you have systems set up that you can do that work on. As I mentioned, there's 2 major pieces to that HASS integration that I want to cover here today. Most of what I've just discussed is covered in earlier webinars, and you can go back and find the details on those there. Here, I want to focus primarily on really getting the HASS into the production facility. What do you need to worry about? And we're going to look at the physical integration, things like selecting the system that you're going to use. What do you need to worry about for facilities and utilities and product handling? And then we'll talk, as I mentioned, about the integration into the production test plan. Where do we put HASS in production? Most people, when they think of HASS, think of doing it just before it goes in the box and gets shipped. That may or may not make sense, and we'll talk about when it does and when it doesn't. And very importantly, what do you do with failures that you find in HASS? What's the best way to respond and why? So let's get into the physical integration portion first. Talk about system selection, nitrogen, compressed air, all the key facilities, venting, and electrical. Now, selecting the right system to do HASS in is critical. You may have a HALT chamber or have used a HALT chamber in a lab that is certainly adequate for doing the HALT in, but it may not be the best HASS system configuration. There are systems better for high volume HASS, depending on product configuration. Key things you need to look at. Am I going to be able to fit this into my manufacturing environment and use it easily? There's doors on these that open out, and once you get both doors open, there's a lot of floor space involved. Look at numbers like floor space per unit tested and cost per unit tested, not only of implementation, but of utilities as an ongoing cost. And of course, time per unit tested. What is the throughput of the system you've chosen? And make sure that all of this meets the requirements that you have set up. Here's an example of HASS implemented in what you think of as a typical HALT chamber. This is a Qualmark Typhoon 3.0, I believe. It's a 3-foot by 3-foot table. And this is in a facility that is doing high mix, low volume specialty power supplies for the military. So we have a test rack here by the chamber, and here is one configuration of power supply being tested with ducting being used to direct air down onto the product. In a relatively low volume environment, this works great, but you can imagine that there's some variability here in placement of ducts and other things that may affect uniformity. You can detect and compensate for that as you set up for each run if you have the time and has the luxury of being able to manage those details. When you get into higher volume of the same type of product, then it makes sense to start looking at a system that's really designed specifically for HASS. And here we have Walmart's newest chamber, our Q Fusion. As you can see, there's 6 separate vibration tables here, and you can essentially design a fixture that is duplicated 6 times for these 6 segments, and have very fast load and unload times. There's slots in the back to accommodate interfaces to test equipment for each one of the slots so that everything can be moved in and out and hooked up quickly and easily. Also, we had a side view, you'd see that this is a fairly shallow unit. It's half as deep as our larger Typhoon 4 chamber. And so it doesn't take much floor space. It's been designed specifically for HASS use, which means we've lowered the absolute thermal range requirements and reduced the vibration range requirements to levels that you typically see in HASS, and realized some cost savings there as well as operating savings. So it makes it a very good unit from a price standpoint for doing HASS in. And here's a couple of pictures of how folks have integrated it here. And here you see racks of power supplies that are mounted into a system. And then on this side, we have large panels laid flat, actually stacked 3 high in these fixtures, so that we're able to test 27 units at a time. No, I'm sorry, 6 times 3 is only 18. It's early in the morning. 18 units at a time there. So let's talk a little bit about some of these facilities considerations. Liquid nitrogen, if you were getting away with using dewars in HALT, which are the portable tanks, you probably won't be able to get away with that in HASS. You're using more nitrogen, and running out of nitrogen is a big deal because it shuts down production. So typically you're looking at a bulk tank outside. If you have an existing bulk tank, which many folks do, don't make the mistake of thinking automatically, I can just hook right up to it, it's not an issue. If you have a tank that is being used to generate gas so that you can use it in flow solder, things like that, those typically run at 120, 150 psi. And that's too high of a pressure for our systems. We expect 50 to 70 psi nitrogen. And reducing the pressure on nitrogen is not as easy as doing it on air. As a matter of fact, it can make sense to have an entirely separate dedicated tank for your HASS implementation rather than trying to tap off of your existing tank. That's something the liquid nitrogen suppliers can help you with. And keep in mind that you do need a supply of nitrogen gas for the chamber. It uses a very low volume of gas, but nonetheless, you need to run a line in for it so that it can use the purge to keep condensation down. And to get that in to the chamber from outside, it essentially demands vacuum jacketed piping. Vacuum jacketed piping, for those of you who aren't familiar with it, it's built like a thermos bottle. There's an inner pipe, a vacuum, and an outer pipe. And it is very effective for transporting cryogenic liquids. It's also more expensive than a copper pipe with insulation wrapped around it, but it gives you a higher quality nitrogen. There's 2 key advantages to going with vacuum jacketed. Number 1, you'll get nitrogen that has fewer bubbles in it. Anytime nitrogen warms up a little bit, it makes bubbles. When it gets bubbles, it confuses the control system. And with the control system confused, you wind up using more liquid nitrogen. And the other thing, of course, is that liquid nitrogen is expensive, and when it evaporates, it's wasted. So anywhere you're making frost, you are wasting money. And then that frost will promptly turn into water during the night, produce slip hazards in the morning. So vacuum jacketed piping will take care of a lot of that. And remember, as you put in that vacuum jacketed piping, to plan for possible future expansion. It isn't expensive to end your vacuum jacketed line with a fitting that will allow the line to be expanded later. If you don't do that, then it is expensive to add on future chambers, because once that vacuum jacketed piping is built, it's in that configuration, and you can't cut it up and modify it in the field. So putting a bayonet fitting at the end of your line can make sense, so that as production goes up or another product comes online, you'll be able to expand that piping without too much trouble. And here's a graphic that gives you an idea of the basic key components that are in a liquid nitrogen installation. We've got our tank outside, we've got a vaporizer so that we can have a little bit of gas for the top of the chamber. Don't need very much, but you do need some. And this also shows some key things like a keep full here to vent out the bubbles that do form, so that you're guaranteed high quality nitrogen coming down into the chamber. And all the appropriate pop-off valves, so that when you shut valves, you don't ever have a potential to trap liquid in a portion of the piping. An oxygen sensor is important. Nitrogen itself, of course, isn't dangerous. 80% of what we breathe is nitrogen, and it's only a problem when 100% of what we're breathing is nitrogen. And that's what the oxygen alarm is for, in case there's a spill or a leak and you have an oxygen depletion situation. And this also just gives you a schematic of how the liquid nitrogen is controlled by our system on the top of the chamber. We have two valves actually, one for a main on-off valve, a redundant safety valve when we're shut off, and another that does the actual proportional control of the liquid nitrogen into the chamber. And you'll also see indicated here the other thing we'll talk about, which is the vent for the chamber. All that liquid's coming in, we have to be able to vent the nitrogen gas out. And here's a photo of an example of a bulk tank installation. You can see here vacuum jacketed piping coming up and into the facility. And this is what will keep you from having ice balls outside. Here in Colorado, we don't have to worry about that too much. I think today we're supposed to hit 10% for humidity. That's why all the fires are burning so well. But in other places, you do indeed have problems with ice balls, and if you go with the liquid nitrogen piping, those problems go away. Now, one of the things that can happen in HASS is you will have more than one chamber. You're looking at 2, maybe 3 chambers to meet your production needs. And people will worry about floor loading, especially folks who are familiar with electrodynamic shakers, and they're saying all these vibration systems here might be an issue because of the vibration into the floor. Fortunately, with repetitive shock machines, that's not an issue. You just have to be able to support the weight of the chamber. The vibration is isolated from the system structure. The whole vibration table is mounted on springs. So there isn't that equivalent downward force into the floor that you have with electrodynamic shakers. So, and no custom floor construction is necessary. As a matter of fact, it's very unlikely that the vibration from the units will affect any nearby processes or workers, unless you have really fine processes going on that are very sensitive to vibration. Keep in mind noise levels. With Qualmark systems, we've got the quietest systems on the market, so noise levels during vibration aren't an issue. If you're running one on a production floor, it won't be any worse than anything else on the production floor, even at maximum Gs. And the nice thing about HASS is you're very rarely running that high of a G level. If you remember the rule of thumb, you're running about half of what the vibration was that you used for maximum in HALT. So the noise levels aren't much of a concern with our systems. We'll talk a little bit about the compressed air requirements, just because if you read the manual and see the compressed air requirements for one of our systems, you're seeing the requirements that are necessary to hit the maximum vibration levels. If you're doing HASS, you're typically running at much lower vibration levels. And the consumption of air is not linear with vibration levels. Getting those last 10 or 20 Gs takes about the last 30 or 40% of the air consumption. So if you're running at half level, half maximum level, when you're doing your HASS, you'll be using much less than half of those maximum airflow requirements. So if you're buying a compressor for 3 chambers, you don't need to take that maximum level, multiply it by 3, and spend a whole bunch of money on a compressor. And one of the ways to figure that out is, as we're doing HALT and you're doing proof of screen, keep an eye on the vibration throttle settings. You can see those on the control screen here. They're also could be recorded in the log files, and you can see at what throttle level the chamber is operating to reach the G level that you've specified. So that number will tell you, in general, a percentage of total maximum flow that is being used at any given time. So if you know you never get above 15% throttle when you're running your HASS screen, there's no point in planning on more than 20 or 25% of that maximum airflow requirement being needed. So that can reduce the cost of your compressor quite a bit in half. In venting, if you've vented HALT chambers before in your facility and your facilities man is familiar with that stuff, then you won't be surprised. But it's different than the typical venting that you think of. You've got a cold gas under pressure being vented out only during cold cycles. And so if you have multiple systems, you can't tie them all together into the same vent line, because one system will pressurize the other. And even with dampers in place, if you have 2 venting at the same time, then there's more pressure to overcome for the second one, and you'll have more pressure inside that chamber. So it can mess things up for you if you try to run everything into the same vent. Also, you're often tempted to say, look, I've got this big in-house vent system because I have hoods over all my reflow lines and everything, so I'm just going to pump it into those. Well, once again, you're under pressure and you've got a cryogenic cold gas, and you'll have a mess on your hands if you try to do that. There are ways to do it. We can help you with that if that's definitely the most economical way for you to go. But if you can get away with having a separate roof penetration for each chamber, that's the easiest and way to make sure you're going to have the fewest problems with venting issues. Now the electrical, well, we can't say the same thing about electrical as we say for the compressed air. You've got to look at the total requirements and add them up, because when you're at 100% throttle in heat, which you will be for short periods of time during your rapid thermal ramps, you'll be pulling that full load. So keep that in mind. Take a look at what's specified. That's a good way to get an idea of the efficiency of a chamber and how much it's going to cost to be running it, is by looking at what the power requirements are, the input power requirements. So keep that in mind as you are looking for a chamber to do HASS in. And as long as you're running all those big fat wires, it might make sense to run enough for a 3rd chamber if you're running for 2, because it's cheaper to do it then than it is to add it in later. The next step you'll need to worry about is getting the system integrated with your automated test equipment. The Qualmark controller provides a couple of software packages, or Qualmark provides a couple of packages for their controller that can help you link the 2 together. We have a package that provides you with a set of LabVIEW drivers that will communicate directly with the PLC controller and the control panel on the chamber, and allow you to write software that essentially eliminates the computer interface that you normally look at when you're running the chamber, and incorporates that entirely into your ATE software. We also have a set of software that will transmit out the Ethernet port, just simple serial strings of data, and receive serial commands so that you can do remote control and remote monitoring of your system that way. But getting all that linked up and functional is a critical piece, obviously, of getting HASS integrated into the system. And when if Qualmark is working with you to do the integration, this is one of the pieces that we make sure is working and work with you to debug if there are issues. So we can help you there as well. And here's a typical HASS setup, if you will, when they've got the chamber here with units under test, driven by an AC source controlled by their ATE here, and then communication here into the chamber for control, and data collection here so that they're able to link together the data they're getting and the status of the chamber at the time, and control the chamber and shut it down as necessary if they're having failures in their systems, their units under test. So let me move on and talk about integrating the system into your production test plan. And the first thing I want to talk about there is process flow integration. As I mentioned when I started, often people think of just testing that full assembly, the final assembly just before it's ready to get out the door. That may or may not be the ideal place to put HASS, and there's some careful consideration that needs to be done because there's trade-offs all the way through that decision. If you have 3 or 4 major sub-assemblies in your device, and these are circuit cards or enclosed devices that have inputs and outputs that connect to the other cards, and you can effectively test each one of those sub-assemblies, do a functional test on each one of them, then you will get a much more effective HASS if you're able to stress those independently. Typically, that external housing of the full-up assembly will dampen vibration quite a bit, will cut down thermal ramp rates so that you don't get as much stress on those sub-assemblies when they're incorporated in the final product. So it's often a trade-off between the effectiveness of the stress and the effectiveness of the functional test. If I cannot fully functionally test a sub-assembly unless it is connected to another assembly that has to be 2 inches away from it, then I can't do that. But maybe it does make sense to take lots of some sub-assemblies and do them as lots, and then look at the full-up assembly, and maybe you don't even need to do HASS at that full-up level. Or maybe there's a reduced stress HASS that you do at that full-up level. Think about it. There's not a fixed statement to be said about this. It involves trade-offs and needs to be thought about for your unit. Don't automatically assume that you're going to do it on the final unit, because one of the nice things is, if you don't do it on the final full-up unit, you don't have to worry so much about scratching things. And that, of course, as we all know, is a big no-no. And to be able to eliminate those cosmetic concerns by not putting on the final case until it's ready to go in the box, you've eliminated yourself some headaches. And the fixture complexity can go either way, depending on how hard it is to fixture your full-up assembly versus how hard it is to fixture those sub-assemblies. That's something to work into your decision-making. If you're doing sub-assemblies, you'll probably increase your throughput because the sub-assemblies are smaller and probably easier to fixture many of them into a chamber than it is for the full-up assembly. So there are several trade-offs to consider, and they should be considered as you decide where is the best place to put HASS. You may look at all of this and come to the conclusion that the best place to put HASS is at your vendor's facility, so that you don't fool with it at all. All you get in are sub-assemblies that are fully HASSed and you've looked at all those results, and you have a confidence level that what you're getting is fully HASSed and reliable. And now I'd like to talk some about maximizing the value of the HASS results. And this is, it's almost a philosophical shift that can come into a company when they have implemented HALT and when they have implemented HASS, and you begin to realize how valuable a failure mode is. To have a failure mode in your hands that you can look at, understand, and eliminate is it's like a piece of gold for your company, because it gives you an opportunity to make sure that those failures don't get in the customer's hands. Now, I'm sure most of you are familiar with the concept of a FRACAS, Failure Reporting Analysis and Corrective Action System, which is, I'm glad they made an acronym for it. And the goal there is to take failure modes, understand them, correct them, and store that information. Close the loop so that you can not make that mistake again and make sure that every failure is understood. The problem is that often FRACAS is not implemented as fully as it can be, or because you'll have in your field service depot, there's a barrel where the bad units go in, and nobody ever digs into them to understand what the failure modes were. And in production, if a unit fails and they take a pass at fixing it and it fails again, then it goes in the trash can. And there isn't a concerted effort to understand what happens and get rid of it. With HASS, there's the extreme stresses that are used in HASS can show you the tails of a distribution that is shifting in your production. And if you take those red flag warnings and toss them in the trash can instead of getting them fed into your FRACAS and understanding what's happening with it, then you're losing a lot of the value that can come out of HASS. And here's another poll that we'd like you to check off for us. And as I recall, you can check off more than one here, so you can, if it makes sense, to select more than one. But really, I'm just curious right now, when you see failures on the production line, what level of failure analysis goes into looking at that unit? Often I find medical companies pay more attention to it because the FDA forces them to, but it can be an extremely valuable thing for anybody to do. So you see some various options there. If indeed it's just a question of 2 times through it still doesn't work in the trash can, and that's checkbox number 1. If you go to the point of saying everything gets into FRACAS and everything is understood, then please check that box as well. And I'll wait until we get a few more respondents, and we'll take a look at the results. FRACAS is it can be a personnel-intensive operation. It requires understanding of failures, and that takes head-scratching and time. But the value that you get from it far exceeds what you put into it. It's always a positive return when you can get a failure mode, understand it, and eliminate it. That's what HALT and HASS are all about, and FRACAS is about doing that kind of understanding anywhere you can get a failure in your hands. So let's take a look at what we have for results here. Well, that's good to see. Looks like about 1/3 of us are actually getting down to root cause on those failures that are happening, and another 20% are certainly investigating. 10%, and it's also, I suppose, is going to depend on how expensive the product is you're producing and how tolerant you can be of failures. I see a 25% tracking everything in FRACAS. So that's good to see. And you can see also, I suspect, as outputs out of both FRACAS and the root cause, that gets pushed to engineering or gets pushed to the vendor for further corrective action. So that's interesting. That's good to see. And I do want to take a little time to look at all the various inputs to FRACAS in a production facility. And we talk about closing the loop here. And there are so many places where you can get information that I really couldn't figure out a way to make this graphic any cleaner, because we can go from the point of the design of the product, looking at doing halts at the subassembly, doing accelerated life testing, reliability growth testing, all the places where we can fail a product, and bringing all of that back into FRACAS, and then feeding that into updating your FMEA or your FAMICA. And then, of course, making the corrective changes, corrective actions as necessary. And here's the big one that so many people have trouble with, and that is a database. Let's remember, it's funny, it's human nature. If it's a failure, you don't want to remember it. But if you remember it, you won't do it again. So you got to have the database that records the things that you don't want to do again. And in the sections that I'm talking about, there's 3 major areas that things will drop out in production. Of course, you have your in-circuit testing, or the equivalent, the first testing that you do on a subassembly, where you can track some things down that will be of value. And then, of course, have I got it in HASS and found an issue there? Make sure those failures get in here. It's very important that the HASS failures are jumped on and understood. And once you come out of HASS, there's a typical final test that will happen. So you'll do the last turn on and watch all the lights come on. Failures there, coming down into FRACAS. And worst of all, if you actually get them in the customer's hands, whatever you do, don't let them put those in the barrel in the field repair depot. Let's get those into the system and understood. Those are the ones those are dollars in that barrel, and they've got to be understood in order to be eliminated. In HASS, it can be particularly important that you get down to that root cause analysis on all these failures. As I say, a HASS failure is an early warning sign of a potentially significant field upset. There can be, you're catching the fringes of distributions when you push out in HASS. And if something has shifted at a vendor's facility, you can spot it in HASS. And if you say, well, that's kind of a weird failure, let's see if it pops up again, and then make a decision on it, can be an extremely dangerous line of thought, an expensive line of thought. Now, if you've implemented HASA, a highly accelerated stress audit, where you're just taking a sample of product and running them through the stresses, then you really have heightened importance of failure analysis, and the speed of the response becomes critical. In HASS, that's important. In HASA, it's really important that the failures are responded to quickly, because if there's something going on, you're busy putting those units in stock and shipping them to customers. The whole time you're trying to figure out what's happened. And so the faster you respond, the more you reduce your exposure to that failure mode. Now, one thing we've talked about a few times before, I haven't mentioned in today so far, is the idea of key performance indicators, or using, these are used like prognostics are used for indicating wear in the field. If you have found during HALT that there are parameters to monitor during functional test that can indicate a tendency to failure or a potential for failure, like noise on a line or timing getting close, or some other performance indicator that lets you know this unit is starting to behave poorly, it's not quite failed, but it's starting to behave poorly. In HALT, you can find out if those indicators are linked to hard failures and are valuable for determining if a product is marginal. If you found out that they are, utilizing those in HASS essentially widens your net. It makes all the testing more effective because you've found some new ways to catch what might be an issue on a product. So, basically, to give you a recap, HASS is very different from the traditional burn-in or ESS that you're used to doing. So education is important in order to get it effectively implemented. And HASS systems are very different from the typical thermal systems that you're used to installing and using. So a day of education and having somebody you can call to help you out as you go through this process is very important. Take a look carefully at what kind of system makes sense. Do I want to move into a HASS-specific system? Is that the most cost-effective solution? Make a project team. Approach the whole thing as a project to get all the disciplines involved that are necessary so that you can get it implemented quickly and smoothly. Make sure you've got all those facility requirements taken care of. And get your head around the idea that just passing a test isn't, it's good it passes the test, but if you can get a failure mode and get rid of it, that's really valuable. And to ignore a failure mode is throwing money down the drain. So to get the full value from HASS, you need to understand that detail. And once you've got the full value from HASS, it really produces the results you're looking for. Reduced warranty costs, improved product reliability, and we all want the customers happy. If the customer ain't happy, ain't nobody happy. And that concludes my presentation. I think we've been collecting a few questions as we went along, and this is a good time to type in an additional question if one's come up. Gail, what have we got?
One thing that I would like to ask you to just briefly explain, there were a couple of slides in there that referred to HASS and HASA interchangeably. Can you define HASA and explain a little bit about when one might want to consider moving from HASS to HASA?
Yeah, I can talk about that a bit, and I probably should apologize. You shouldn't use acronyms without defining them. But HASA is a highly accelerated stress audit. HASS, by definition, being called a screen, implies 100% of the product going through the test. With HASA, we've decided to do an audit. We're taking a sample, and the level of sample that we take is chosen like you choose other sample rates for incoming inspection and such. And you have to look carefully at the risk involved when I am choosing to do just an audit versus the cost involved. If I'm in high volume production on a system that I have got very tight control on my processes, then an audit can be sufficient to catch shifts in that process that you're not catching anywhere else, or to catch shifts in your vendor's process. If you are doing low volume, high dollar, high cost of failure products, those are the ones that you just, there's too much risk in moving to an audit. When you're in low volume environment, there's typically more hand operations. Typically you get jerked around a little bit more by your suppliers because you're ordering in smaller quantities, and there's just too much risk. And if you have a high cost of failure there as well, you really need to be doing every one. But if you have high volumes, good process control, then an audit can save you some money.
Okay, thank you. On slide 10, you spoke briefly about fixturing for HASS. And one of the questions was, well, if Qualmark has designed the fixturing and qualified it, why do we need to repeat it on site?
Yeah, when Qualmark designs a fixture, we will do a validation here, making sure that we're getting the type of response that we want on a system similar to yours. But it isn't yours. And a final check on your systems is important because just to eliminate any possibility of variables and do it with all the final cabling hooked up and perhaps for the first time with true final product in there, all the things that might shift it are taken into consideration so that we get a final check on it to make sure everything's right in its end-use environment.
When would it be better to use a larger HALT HASS chamber, or when would I want to switch to Q-Fusion for HASS?
Actually, the biggest thing to look at is how big your product is. With the Q-Fusion chamber, as you can see, as it's designed, there's not a lot of headroom above in each one of those compartments. It meets the reason we designed it at that height is because it's met the vast majority of the needs. But if you have a larger system, you can look at a custom Q-Fusion chamber that has fewer tables or something like that, but that's a longer-term project. May make more sense from a dollar standpoint to just look at a standard chamber and move into HASS there. And but that's the primary requirement. The other thing is that if you are doing production for example, downhole tools or other things that require really extreme temperatures for a production test, then the Q-Fusion may not have the temperature range to run it.
For documentation and reference material, I do want to say that Qualmark does publish HALT HASA guidelines on our website, www.qualmark.com/HASS guidelines. You can request it from there. We also offer it available through our library. I'm just looking down through here. Neil, we have some facility integration documentation.
Yeah, we have our site preparation manual. I don't believe that's available online, but certainly it can be requested, and when you're getting a chamber, that's one of the first things we try to put in your hands is the site prep manual. And it has all the details from how big the crate is and how heavy it is so that you can get it in the back door, down to the heights of all the connections for the liquid and the gases and everything else on the chamber. Everything is in there that you need to know, like the flow rates on the nitrogen and the flow rates on the liquid or on the compressed air and all the rest. So that's a key document to have in your hands as you begin the integration process. I say I've got just takes a minute to discuss the kind of the third option for liquid nitrogen storage between dewars and the big tank outside. I see a question about a micro bulk, which is a nice option depending on the volume that you're doing. A micro bulk is kind of a cross between a big bulk tank and a dewar. Built like a dewar, it sits inside, freestanding on the floor, so it doesn't require building permits to put in, but it is filled from the outside, so a truck can come and fill it from outside. Takes up some floor space. Typically, I think you've got 2,000 liters as an option for a micro bulk, so they're reasonably big. They're a nice option if they will meet your needs for total liquid nitrogen usage.
At this time, I'd like to thank you, Neil, and thanks to everyone for your participation today. I'd like to remind you again that Qualmark supports many opportunities for learning about HALT and HASS, from beginners all the way on to experienced hands, and how to improve and optimize the results from your accelerated reliability testing program. So be sure and visit our online resources tab section. Reach out to the Center of Excellence for Professional Services. Very steady hands in helping you guide and support any aspect of your HALT or HASS program. This has been the fourth in our HASS series. We plan to conclude the series next month. We'll be looking at HASS documentation. So be on the lookout for your invitation in your email box, or as always, keep your eye on the home page in the Spotlight section, and you'll see the announcement of upcoming events. And once we get the next month's webinar completed and planned, we'll post that link for registration there. And again, I thank you everyone for attending Qualmark's Ask the Experts presentation today.
Thank you, Gail.